I'm happy to be back here and have the opportunity to share with you guys this project that I had the chance to collaborate with University of Minnesota, with Bob, with Carl, and also with the IO Select team. And the objective here was to try to go a little bit deep on the mortality that were affecting the closeout at the closeout level. So from winning to finishing stage, and because of some variability on both on mortality and also variability of being infected or not with 174 kind of virus, variability of guilt type, and other variations that we found in the system, we were able to construct a model to try to predict the mortality. And for the purpose of this presentation here, try to understand how measure the relative importance of the different factors, and most importantly, the effect of the 174 type of virus on the mortality in this database that we're going to talk about right now. So before that, just a couple of slides on the methods here. This is a example of work of field, what we call field epidemiology, which is putting together all the information available from diagnostics, from clinics, from pathology, from the numbers, and put those together, combine them in a data set so that we are able to run some models to understand what happened. And why do we want to understand what happened? Because we want to go further and explore some interventions to change that predicted high mortality or predicted bad event. So our idea was to describe what happened, see how good we were in predicting, and be able to, from now on, using this information, select the best intervention methods to try to influence the outcome. So goals here for this analysis were two. As I said, one, understand the variability in the win-to-finish mortality. What were the contributing factors and what were the relative importance of each. And for this presentation here, for this panel, assess the role of being infected with 174, what that contributed to the mortality, and of course the economic outcome at the end of the day. Those materials and methods, we developed this statistical model to combine information from different sources to explain the mortality. We took information from the swine health information from the swine health monitoring project, meaning we were interested to map the sow farms where they status 1 to V, 4 for PRRS, for PED. Also took selected sow farm parameters. We're going to talk about the significant ones in a little bit. Also some management parameters, and of course the closeout itself. So what was the start date, the start weight, and other variables that were there available in the meta farms. Combined all those different spreadsheets and different information in a single spreadsheet that had about 200 or 2,000 closeouts, some 7 million pigs starting there, and from 41 different sow farms. To be able, of course, to associate the 174 or the PRRS status from the sow farm to the closeout, we selected to work only with the single source closeout, because it makes sense. With that, we would able to merge the swine health information project with the sow farms, and also to make more specific the study, and because of some characteristics of the system, we also selected to work and focus on the win-to-finish closeouts, not nursery, not finishing, not other types of growing. Only so from this initial data set, we cleaned up and worked specifically with 462 closeout, which were about representing about 2 million pigs from 33 sources, single sources. The analyses were done in SAS. If anyone is interested, the models are constructed, and we'll actually be happy to see how we can extrapolate that information to other systems. We'll be happy to run this model in other populations and see how good we are in extrapolating this specific model. But just to give you an idea here of the variability of the mortality that we were dealing with, this is the distribution of the mortality between the sites that we worked with, and those are this is the actual mortality. And for those of you that are more familiar with statistics, when we run most models, we need somehow normal distributed data. This was not normal distributed, but we log transformed the mortality. So those are pretty much the same data, but in the log scale or log world. And as you can see, it has this so-called bell-shaped or normal distributed, which allowed us to use statistical tools to predict what happened with the data. And pretty much you see here minus 2.8, that's in the log world, but it means some 6.5%. And at the end of the distributions here, the extremes, we're talking about some 1.2 to 30%, which, so this variability allows us to try to find the risk factors and measure the relative importance of each risk factors on that variation. And our objective when we started the model was, can we predict, do we know how to explain why some closeouts were here while some other closeouts were there? And if so, what can we do to influence that, to prevent closeouts here and replicate more closeouts like that? So we run several univariate models here and selected the ones that were significant or tended to be significant in the univariate analysis to build the final multivariate model. And by at this stage, we selected the ones with yes here were the ones that had p-value less than 0.1 to move forward, and with trend the ones with p-value less than 0.2. So, and the ones that, of course, that were not significant, we just removed and did not consider in the final model. Before showing the final model, I'd like to show selected univariate analysis here for the main variables that we investigated. On per status, you see here the distribution of mortality. So in the y-axis here, you have the mortality, and you have here the distribution of mortality of the flows that came from sow farms classified as status 1 in the swine health monitoring project, meaning positive stable for PRRS virus. And here the distribution of 2V and 4, and you see here a trend showing here that as farms move from 1 to 2VX to 4, mortality went down. And we did similar thing here, but we were interested here in this slide on the effect of 174. So those were the flows positive for 17, or classified as 174 flows. And those were positive for PRRS, but other, not 174 kind of PRRS. And those were flows not classified as not active for PRRS virus. You see here how mortality went over time. So you have here mortality over time by quarters, 2014 quarter 1 to 2015 quarter 2, and the boxes there represent the PRRS type here. So you see that consistently the green boxes, which we call the bad PRRS, the 174 PRRS, it was higher and with higher variability when compared to other kind of PRRS and also the negative flows. We also looking now at PED status. The difference was not that significant. We had some trends going on here, but the take home here, this is not about PED. It's just that we adjusted our analysis to the PED status. We also found an important variation of mortality when adjusted by feed mills and supervisors. Adjusted by everything else, some feed mills were associated with lower mortality, as low as some average, some feed mills with some average 2%, some others with 9%. So there was an important effect there. Similarly, with supervisors, some supervisors that had the adjusted mortality below 2%, some others that had really high mortality. And so we wanted to adjust the model for that, so included that in the model, not to identify here who are the best or who are the worst. That's a different story, but we did adjust the data for that. Same here for guild program type. There was some trend here of selected a specific guild type had a little bit lower mortality than the ones that, so the bread guilds, sows that received bread guilds had a little bit lower mortality than the ones with that received guilds at 240 pounds. So let's jump to the conclusions here. The model that we constructed, when we compare what actually happened, the actual mortality, the real mortality here, and so we did all that in the log world and back transformed to the so-called the geometric mean, or bringing them to the actual to the numbers that make sense to us. Here we plotted the actual mortality against the mortality predicted by the model, and we were able to predict the model explained some around 80% of the variability. Had an R squared of 0.81, and this final model had the PRRS, of course, the PRRS virus, if it was 174, or other virus or none. Weeks on PRRS status was also important, meaning if you were status 4, and you got infected, it had a difference of being infected at the first week or second week, or or 10 or 12 or 20 weeks after changing status. So we adjusted for that. Same thing if you were so yeah, let's leave it like that. It was important the weeks on the PRRS status, and we nested that with source. The start quarter, you also saw that there was a difference between the status, the start quarter, the year quarter, so a time variable here. We adjusted for that. Also adjusted for guild type, supervisor, feed mill, PED, and percentage utilization. But we were quite satisfied with the model predictability here, and looking specifically here at what we started discussing, what was the relative importance of being infected with 174, and how did 174 contribute to the mortality. We concluded the model showed in that time frame about a year, some 52 weeks of closeouts. And in August now, at the end of August, we saw that there was no statistical difference between being classified as PRRS negative and being infected with other PRRS virus other than 174. But the 174 flows had additional 4.8 mortality compared to other PRRS viruses. And using a very similar model with pretty much same variables, we constructed a model not to predict mortality, but to predict the actual profit or loss. And the model had a similar R squared, and it showed that the 174 PRRS flows, there was a loss or decrease in $2.87 at the end of the day. So as a conclusion here, model accounted for 81% of the observed variability, and win to finish mortality was increased significantly when it was infected with 174 PRRS, 4.8 additional mortality, and which were also associated with a reduction in $2.87 of profit, those closeouts that we follow.